Well, good afternoon. Let's go ahead and get started. Welcome back to another day of Chemistry 401. Does anybody have any questions before we get started? So we are in the heart of the material for Chemistry 401. And if at the beginning of lecture somebody had a question that was covering something on the homework, then I could do something along those lines. We probably have to keep it to about 5 minutes, but 5 minutes you can do a lot of homework. So keep that in mind for Monday. Keep that in mind in general. Doesn't do you much good next Wednesday, at least for current homework, because homework is due next Wednesday at 12:30. Okay. Well, where were we? Last lecture was all about buffers. And what we decided, or what I tried to tell you at least, I don't know if we decided it, was that a buffer is a solution of a weak acid and a conjugate weak base. And there's a couple different ways to make a buffer, and we'll see some of that today. But you can put the weak acid and the conjugate weak base into solution, done. You can also put a weak acid and some strong base. The strong base will react with the weak acid and turn it into weak base, weak acid, conjugate weak base, buffer. And of course, you can have a weak base, add some strong acid to make the weak acid as well. So, and you'll see that on the homework. Homework 4, actually I've made it. I was supposed to be here today because I order it photocopied from the main campus. I know, anyway, I apologize for not having it to hand out today. But what I'll do is I will definitely put it on the Chem 401 website, and then I will plan on bringing it on Monday. And if I get it sooner, I'll put it in the box, the graded papers box outside my door. Cool. Okay, well, then the next topic in Chapter 17 is titrations. We talked about titrations in Chem 400, although the only type of titration we did in Chem 400 was strong acid, strong base. Okay? And that's going to be our starting point here, strong acid, strong base. Before we talk about that, just a little review. Equivalence point, the point at which equivalent moles of acid and base have been added. End point, a change in the physical properties of a solution in response to reaching the equivalence point. Well, that's something different, I guess. Must be the equivalence point. Often a color change for acid-base titrations, although there are other kinds of titrations as well that you may or may not see once you get to organic chemistry. Specifically, redox titrations, where you're looking at changes in oxidation state, and sometimes those lead to changes in color as well. All right, so with that, our first type of titration is strong acid, strong base. We'll do a little bit of chemistry Mad Libs here. Can somebody tell me a favorite strong acid that they have? Kate?
Hydrochloric acid.
What's that? Hydrochloric acid, one of my favorites as well. Does anybody else have a favorite strong base? Dylan?
Sodium hydroxide.
Sodium hydroxide. The point I'm making here is that it doesn't matter what strong acid or strong base you use here, the process is going to be the same, because the strong acid dissociates 100% into, well, we used to call them H pluses in Chem 400. Now the equivalent concept is hydronium, H3O plus now. Let me finish my reaction first here. HCl plus NaOH is going to make H2O plus sodium chloride. Nothing changed there. The one thing that does change, at least now, and it's a minor change, is, well, you could do this with H plus OH minus. I'm going to do it with hydronium this time because that's our Chem 401 interpretation. So we get hydronium, and that's a direct result of the fact that we have Ka reactions now. Remember, a Ka reaction says acid plus water goes to hydronium plus conjugate weak base. So these are the products of our Ka reaction. That's another way of thinking about it. Okay, so good. I think my net ionic equation is going to turn out to be a little lower here because this is looking so far more like a total ionic equation. Luckily, I think I left enough space to do this. Sodium hydroxide, sure enough, becomes sodium ions and hydroxide ions. To make this a true total ionic, and this is an ad lib, making it up as I go. There we go. Put all the states in there, charges, etc., etc. I guess there should be one more plus there. In true total ionic fashion, the H2O, the liquid, solids, and gases drop right down. There's nothing to break up into parts. Oh. Well. Something is amiss, by the way. Can anybody tell me what's missing from that H2O according to writing the hydronium right there? That's you. Now it's balanced and everybody's happy. I know. But then, so we take the Cl minus, it's on both sides. We take the sodium plus, it's on both sides. And we're left with the NIE now, hydronium plus hydroxide. And I'm back in equilibrium lingo here with the double arrow. A couple people have asked me about whether I care about double or single arrows. In Chemistry 401, you can always put a double arrow because everything is at equilibrium. On the discussion, sometimes we had you put a single arrow. You can use that when a reaction goes to completion to help you, but I will never grade your arrows. I will always ask you sufficient questions to know what, what's going on. Question, Dylan?
So even if the Ka value is like 10 to the 18th, you still wouldn't mind if we put an equilibrium arrow?
Question, if the Ka is 10, or any K is 10 to the plus 18, would I mind if you put a double arrow? No. That's just me. Well, and as you can see, I sprinkle my double and my single arrows quite liberally anyway, so I guess that's, hopefully, I don't ask anything of you that I'm not asking myself. Anyway, now there's two waters over here. And that's the net ionic equation. My next question for you is what is the Kc value for that? If I write an equation, pretty much in Chem 401, especially now that we're finished with kinetics, we can ask what is the K, since this is not a Ka or a Kb reaction. Remember, if it was a Ka or a Kb, one of these would have to be water on the reactant side. That's how we know it's not Ka, Kb. However, does this reaction look similar to something else we already know? And if so, what? It looks like Kw, except not exactly. What's happened to the reactants and products? They've been reversed. So the Kc for this is not equal to Kw, it's equal to 1 over Kw, or the reciprocal of Kw. And since Kw is 1.0 times 10 to the minus 14, what is Kc for this? We'll treat that as a rhetorical question. I'm sure you know the answer. It is 1.0 times 10 to the plus 14. Does this reaction go to completion? Yes. Of course, you don't need the plus sign because it's implied even if it's not there, but since plus signs are a little unusual there, I put it in. It is a plus sign. This reaction does go to completion. And yes, I did use a double arrow for this, even though it's 10 to the plus 14. Anna?
Can you reiterate why it's 1 over PW?
Sure. So I would suggest that we've seen something similar to this before in this. That is the KW reaction.
Oh, okay, so the H2O is on the other side.
We flipped our reactants and products, or reversed them. We reciprocate our KW. Yeah. Any other questions? David?
Would the coefficient of 2 in front of water affect the Kc at all?
Would the coefficient 2 affect the Kc? Well, first off, these are liquids. Liquids don't show up in Kcs. So, and just the bigger picture is that in Chem 400, we would call this 1 H2O goes to H plus hydroxide, and we still used KW for that. And it's as if, and this is this does work, by the way, but it's not something we covered in class. But by subtracting 1 water from this side and subtracting 1 water from that side, even though it's paired up with the H plus, it does work. It's not at all clear necessarily that it does, but it does. Okay. So, does that answer your question? Yes, more or less. Any other questions? Because this, whether, I know you've been paying attention, but one of the underlying things about Chem 401 that was, in Chem 400, every reaction had a delta H. In Chem 401, every reaction has a K value, a Kc or a Kp, or both. And it's oftentimes helpful, even if I don't ask, to think about what the value is. Anyway, so we're going to be touching base with this. I think last time I talked about how we were going to prove that some reactions go to completion and others don't. We have just proved for sure that this reaction goes to completion. All right, now what is the pH? Next slide. What is the pH when 10, 20, 30, and 40 milliliters of 0.150 molar? Well, here we'll plug in for this first blank, we'll actually put our sodium hydroxide. For our second blank, we'll actually put our HCl. And these are identical to problems we did in Chem 400. And so they will all be companion problems. Which I will post over the next couple days on the Chem 401 website. But we've done these before. In general, they look like this. Find the moles of base, find the moles of acid, whichever one is the excess reactant, find its concentration, and then find either pH or POH, just like we did last semester. So there's nothing new there. Happy to help you with it. Still fair game for your exam, but review. Ooh. Yeah. Well, there's plenty of room in your notes to work on those calculations. Now let's review what a pH titration plot looks like in that case. And this is for a strong acid, strong base. And we're going to do this because we're going to then compare it to the weak acid strong base. And what you need to know is that whatever your starting point is here, as you add strong base, the pH has to go up. But it goes up very slowly, and when you do the calculations, you'll show this. Let me see if I can draw it correctly. Turns out our equivalence point is right here at about 33.33. And that shouldn't be flat, that should still be steadily increasing. So I'll draw a slightly better picture. The pH equals exactly 7.00 at the equivalence point. And that's because at the equivalence point, you have added equal concentrations, or sorry, not equal concentrations, equal number of moles of your HCl and your sodium hydroxide. And at the equivalence point for a strong acid, strong base titration, especially the one we're talking about, the only things you have are sodium ions, chloride ions, and H2O. Sodium ion is an inert acid, no effect on pH. Chloride ion is an inert base, no effect on pH. Water is just water, no effect on pH either. That's why the pH is a perfect 7.00, right? In the acid-base Olympics, 7.00 can be perfect. Any questions about this, Anna Marie?
What is the EP?
EP, equivalence point. And EP for me always stands for equivalence point. Let me note that just to be clear. Because we'll use that again a couple times. And remember, the relationship between the equivalence point and the end point is you hope, cross your fingers, you hope that your end point is the same as your equivalence point, but that's a whole nother conversation. And typically, we make it so, we being whoever designs the labs. Travis?
Can you describe the shape of the graph and why it accelerates so quickly at that 30 millimeter?
Yeah, no, I think it's supposed to be a 33, but anyway, I apologize.
So it's supposed to just go straight up?
But it's supposed to go straight up. That's what we're trying to capture. And actually, let me tell you what we're trying to capture here. Very slow but steady increase. Very sharp increase. And it turns out that this is so steep because you go from having strong acid excess to strong base excess. There's nothing weak here. And so that's why it's so steep.
Oh.
Does that make sense?
So if there were like weaker acids and weaker bases, the steepness would decline?
That's where we're going next, and we'll actually do those calculations. We will see that it will not be as steep.
Oh.
And that it will be dependent upon what is the Ka over weak acid. Yeah. Okay. How do I know is it 33 milliliters? Because I did the companion problems in my head already. Or no, they're actually, some of them are on here, I think. But when you do the companion problems, you should see that it's at 33.30. But what's not, so that the companion problems are review. The shape of this that we're going to relate to the other one, I mean, technically that's review too, but I want to talk more about this, so that's why I'm other questions. Yeah, actually, let me note this. So down here, there's excess strong acid. Up there, there's excess strong base. And as you go from strong acid to strong base, there's a very steep change in pH. Second type of titration, weak acid, strong base. Now we're going to titrate 25 milliliters of 0.1 molar formic acid, not that you have to know its name, there it is, with 0.100 molar sodium hydroxide. Overall reaction given there. Net ionic equation, well, this is a weak acid. From Chem 400, we said that weak acids dissociate less than 5% when placed in water. And we said that in the net ionic equation, you do not break up weak acids or weak bases, but mostly we focused on the weak acids. So weak acid does not break up in net ionic equation. But this process is similar. We're going to take the formic acid. We won't break it up. We'll talk you through it a little bit here. Sodium hydroxide, strong base, breaks up 100% into ions. That sodium ion will be a spectator, so I'm not even going to write it now. That says AQ for aqueous. So it's a little hard to read. So, but we're just keeping our hydroxide. On the product side, on the product side, we have our H2O liquid, and we're going to ignore our sodium again and have our conjugate weak base, the formate ion. And while I encourage you to remove this H from the COOH group, COOH, I remember way back when I first met you on our first day of Chem 400, and I said, remember COOH. Still, you have to. Anyway, but if you take off the H, the other one, I don't really care. I do care that this has a minus and this has a minus. That's going to be helpful to you as well, because that means you should think of this as most likely as a base, because negative ions we typically think of as bases. Anyway, any questions about this NIE, net ionic equation? Okay. Na plus spectator gone. In fact, I cannot think of a single time when we care about the sodium ion for the rest of the semester. Promise. That's what I'm trying to think, if I can promise you that. The equilibrium constant on that is very large, but nothing, no reaction truly goes 100%. So let me think about it, but pretty much. Generally speaking, we'll ignore sodium. Okay, so when we do it here, okay. Any other questions? Because I have a question for you if nobody has a question for me. My question is, what is Kc for this? And when you think about it, before you answer, I know you're all like, can I answer, can I answer? Look for water. Because water is part of a Ka or Kb reaction. Then look what's next to it. Is an acid or a base next to water? It's a base. And so does this look like a Kb reaction backwards? It does. So what is K? It is 1 over, Anna Marie, Kb for formate ion. And since Kb's typically, we don't know the exact one for this, we'll get to it in a minute, but since Kb's are always less than 1 and greater than 10 to the minus 14, but whatever for that part, we know that this Kc is going to be a relatively large number. We will not be surprised. Let's see, Kb, oh yes. Oh yeah. Kb, oh, no. Yeah, it's KB. Good. Okay. And it is. Yeah. 1.8 times 10 to the 10. I wrote my notes in a slightly different fashion. I couldn't find it there for a minute. This gives me time to think sometimes. And then I did. And then my question now for you, does this reaction go to completion?
Yeah.
Based on that K value, yes it does. Good. Okay. And here's what you're going to have to do. So most of the time, actually all of the time, weak acid, strong base will go to completion. And we will be able to treat weak acid, strong base, just like we did strong acid, strong base. If you remember what I at least mentioned for strong acid, strong base, it was find the moles of strong acid, find the mole, or of weak acid, find the moles of strong base, find the limiting reactant, then find what's left over. And that's what we're going to do. But before we do that, let's see. Let's find the initial pH before we add any sodium hydroxide. We'll get there in a minute. I have to admit, I got a little excited there. But for initial pH, before we add any sodium hydroxide, we only have a solution of formic acid. In water. Calc using the K for formic acid. And we'll write out our Ka reaction. Good. Yeah. We look up our Ka value from question.
Why is it plus water?
So question, why is it plus water? Okay, so this is before the titration starts, okay? We have not added any sodium hydroxide, and so this reaction can't happen yet. And so I apologize because I got a little excited. I was so ready to titrate things that I forgot we had to go do this before. Does that answer your question? Yeah. Oddly enough, and this like, I just embodied what I have found the student experience to be, by the way, which is when you get to a problem like this, you, meaning you in general, the royal you, are so excited to titrate that you forget about this part. And I just did it too, so I empathize. In advance for you, whatever that means. We take the concentration of our formic acid, put it into a nice table. And this is a chapter 16 problem. So it's very similar to what you're doing right now. Can we ignore X? I don't know, but I want to.
Try.
And I'm going to try it. It's above the magic 1.0. It's times 10 to the minus 4th, isn't it? So I'm wary. Right? I'm finally paying attention. So, all right. And I'm just going to say what X is. X equals 0.00424. Is that greater than or less than 5% of our initial number? Since it's 4.24%, it is indeed a little less. So we were justified in our calculation, which I was nervous about. pH equals 2.37. Now, if this was a strong acid, and it was 0.1 molarity, do you know what the pH would have been? 0.1 molarity strong acid would be 0.1 molarity H3O plus, and we would have done the negative log of that and gotten 1. So the first thing is, of course, weak acids have higher pHs at the same concentration. That's folded into this. Anyway, now I'm happy to say we can actually start doing some titrating. Are there any questions about this? That problem for chapter 16 is bread and butter. Gotta know how to do that. Now, we'll do some of these. I'll work over here, see if I can keep it going. Let's do 20 milliliters. 20 milliliters. And I'm going to change this to the sodium hydroxide. Add it to 40.0 milliliters of 0.100 molar formic acid. So same system. But in most titrations, you do have a constant amount of weak or acid, and you add varying amounts of sodium hydroxide to it. And I apologize for that.
Professor?
Yes?
What are we doing?
What are we doing?
Yeah, right now, we're looking for Ka first, and then looking for the titration part, or is it, like, looking at it, how do you know what to do?
Good question. So I'm going to take a little bit more of this board space back, and then I'm going to explain. And I'm going to explain the difference between these two, because that's an important thing to think about. In this particular problem, I have sodium hydroxide, and I have formic acid. And that's it. And I have water too, because it's aqueous. So I have three things. And this gets to the heart of how to deal with every single problem, almost every single problem on your second exam, is what do I have and what happens to it? Do I treat it with an ice table? What kind of ice table do I do? And so you need to be able to look at that thing and say, weak acid. Right? And you have some clues. One is, if you're not sure what it is, the formulas are on your conversion equation sheet with their names for the acids, so you can find it out. But this is a weak acid. What's that? Sodium hydroxide. Strong base. and just plain water, right, it's always there. Now, what I proved over here is that weak acid and strong base, based on the Kc value for this, react to completion. Kc is approximately 10 to the plus 10. Now, let me differentiate that from this problem I solved right here. In this problem, I had two things. I had formic acid, a weak acid, and H2O. I had no sodium hydroxide because I told you I haven't added any sodium hydroxide. So for this one, the only thing I can do is a Ka reaction for this. And underlying all this is the fact that I'm always trying to decide really which ice table to do first based on what's the largest value of K. And the largest value of K for this one, with only these two things, is Ka. Now I come over here, I have a weak acid and a strong base. My reaction will go to completion. And then whatever I'm going to do next, let's check in and see if there are any questions about this. Esperanza, what do you think? Cool? Good. Everybody else? Okay. Because this is key to your understanding for the second exam is what do you have, then we'll figure out what to do with it. And really at the heart of it, again, is if you have something strong, whether it's a strong acid or a strong base, there's pretty much going to be a reaction to completion as your next step. Anyway, but we'll see that. Okay. Now, for reactions to completion, you have a mole listed. Because reactions, things that react to completion will react in terms of moles. And there are ways that actually you could do this in terms of molarities, but I think it's harder. And so we're going to do moles. And the reaction to completion will have these two, formic acid and sodium hydroxide. So I got that sodium around. I'm going to ignore it. I'm going to treat it as a spectator. I almost wrote it too, but then I said sodium's going to be a spectator. And I will use my single arrow, although I do not have to. I'm using it because I know this reaction goes to completion. And if you put this in here, it can still work. I would say it's a little more complicated for me, so I like to do the step of leaving it out. But it can still work. In chapters 16 and 17, there's really only one type of reaction. It is an acid-base reaction. Acid-base reactions move a proton from your acid to your base. And I haven't seen a lot of people doing that with their H pluses on their homework. And that's fine, you never have to do it. But for me, it's part of my process to think about things. And so it's also fine if you do it. I add an H plus to hydroxide, I get water. I take away an H plus, I get formate HCOO minus. where that, if you included your sodium, would be sodium formate. And the only problem with including these sodiums, for me, is it's a little harder to see what the Kc value will be for this if there's sodiums in it. But the other alternative is, if you've got a strong base, or, as we'll see, a strong acid, the reaction's going to completion. Just remember that. All right. This will be a mole ice table. We will figure out the moles for our formic acid. We'll write that out, of course, but to save a little time, we'll put it right there. For my 20 milliliters of 0.1 molar sodium hydroxide, like so. And I have plenty of water, but nobody cares because it's a liquid, and I start with no formula. This reaction goes to completion. For ice tables that go to completion, they're typically in moles, but we've seen a couple, especially on this last discussion sheet, where there was a molarity ice table that went to completion. When they go to completion, there are no X's in here. Find your limiting reactant. Lovely. All the coefficients are 1, so we don't have to mess with any coefficients. Add the same amount to our product side. I put squiggly equals 0 here because this reaction, while it does have a very large value of Kc, no reaction truly goes to completion. And there's always a little bit of hydroxide, just like there's always a little bit of hydronium in water, which is really rare. Questions about that? Logan?
We found an initial concentration for HCOO- in the previous problem.
Yes.
Why does that number not matter? Why can we mark it as 0?
Good question. So we had an initial concentration right here of our acetate. In fact, we had one for water as well, hydronium as well. And the short answer is, in this ice table problem, we are starting back at the beginning as if we are just mixing these two things together. And had we included this, well, let's say this. Mathematically, you can totally do it, but mathematically it will be very complicated to do that. Because whereas you have hydronium here, you have hydroxide here, and the more hydroxide you have, the less hydronium you have, so things get wacky.
Yeah.
So think of it as every time you start one of these problems, you're going back to the beginning as the easiest way to handle it. And the math will totally take care of itself that way. Although I can appreciate that it may not be at all clear, but it may not be 100% clear. But that's the easiest way to do it. And that's similar to every single problem we tackle. You do go back to the beginning, and then the largest K, you do an ice table of some sort first, then the next largest K, which we're about to do, you do another ice table, and as long as the K values are pretty far apart, a factor of 1,000 apart, that always works. Even though all of these ice tables are literally happening at the same time. You're mixing them together and everything, done. But you're treating it as if the first thing happens with the largest K, and the next thing, and the next thing. So I don't know if that answers your question, but
Yeah, I guess that makes me confused as to why we did that first ice table, because I thought it was to establish sort of the baseline conditions, what the concentrations of things were at baseline. And if that doesn't matter for doing our technical calculations, then why are we?
Good question. So your question is, why did we do this if it has no effect on that? Is that what your question comes down to?
Yeah.
And I will keep the answer relatively short. I can tell you more after class, but the short answer is we will be interested in the concentration of just a weak acid in solution. That's called Chapter 16. And I wanted to touch base with that as the starting point before we really get into our titration.
So it's not necessarily part of this problem as a whole.
It's not, right, it's like, what is the pH before the titration starts? Marissa?
For like the first problem, why did we set up the Ka reaction, but the second problem, we like added the two of the weak acid and weak bases together, like with five, you know, like why did we convert these two problems differently?
Great question. Why did we approach these two problems differently? And the short answer is, we looked at what we had, and we went with the largest K reaction possible and did it first. And so, with only a weak acid and water,
Our initial like the overall reaction has the weak acid and which one, or sorry, the weak acid and which one base or
good question. Why did we not use this for this ice table? Is that your question? Okay, because we had no hydroxide. And this was very bad teacher form, by the way. I should have done this first and then talked about this. Right? Because there's no, like, I was like, super excited. Yay, weak acid, strong base. Gonna be a weak acid, strong base titration. And then I said, oh, we haven't started the titration yet. So I was like, yay, no. So, and I apologize for that. I know that was confusing, so and I try not to do that, but the reason we came here and did not use this K, this reaction at all, is because we did not have any hydroxide.
We're like titrating the sodium hydroxide into the sodium water.
So let's say this, you've done a titration. The titration goes like this. Measure out your acid, put your base in your burette, and then start adding from the burette, right? This one says, before we add any sodium hydroxide from the burette.
And then the second problem is once we've added the hydroxide to the burette,
What is the pH? Yeah. And again, I apologize for that. I got super excited, should have checked my notes, didn't. Just started rambling. Alondra? Oh, your question is why did we start with 20 instead of any of the other ones? So the answer is we're going to talk about all of them. But this was why did I start with 20? Well, I'm glad you asked. Now, are there any other questions before I keep going with this? Yes, Esperanza.
Why didn't you do anything with KB if we typically found it?
Why did I do nothing with KB?
Yeah, you focus on KA on this portion.
Okay. Why did I focus on K? Because I have an acid, and it's a weak acid. And for this one, I focused on KB, or 1 over KB, because I had a reverse KB reaction. So this reaction over here, it's like, oh, I already wrote that there, but it's 1 over KB, and meaning now we're back to the titration. Okay.
So if you don't do anything with this point five, you only use the first question. The first problem, right?
Yeah.
Can you do that?
Oh, I see another mistake I've made. Let's call that 40. Right, because now it matches over there. We didn't do anything with the 25. I want to titrate 40 milliliters. See, I have 40 milliliters over here. It's a mess, I'm sorry.
This whole process, I guess, is weak acid, strong base, and then vice versa, like, weak base and strong acid too. Like, you know, how you set this all up, or it would
Ah.
be like that for all of them, and then like vice versa.
And then vice versa. So how about this? After we do weak acid, strong base, we can talk about weak base, strong acid. And then weak acid, weak base. We'll hit everything.
So just remember like that setup, it's talks about weak acid, strong base, and then do the mole setup.
Then do the mole setup over here.
Yeah.
And we're not done yet,
Oh,
because we now have formate, and we now have formic acid. This is a weak acid. This is its conjugate weak base. What is this? This is a buffer. So make those notes. We have a weak acid. We have a conjugate weak base. We have a buffer.
What is the buffer?
Oh, buffer is just see, downstairs they have the walls you can write on. I don't think I can write on these walls, or I can, but it won't be erasable. That's what I'm sorry. Now it's not has nothing to do with the water, is what I'm trying to say. But do you remember how we solve all buffer problems for Monday? It's this equation that I don't like to say its name. Anderson-Hassel-Bouch. And it goes like this: pH equals pKa. Plus log of the conjugate weak base over the weak acid. We said on Monday that I'm writing it this way because those could be moles of conjugate weak base over moles of weak acid. They could be molarity of conjugate weak base over molarity of weak acid. So I'm just putting the names there. And if your question is, why do we do this next? It turns out that after this reaction with a Kc of 10 to the plus 10, the next biggest K value is Ka. Ka for our acid. And the next biggest, the one that's always the smallest, in fact, is the pH one. pH is related to the Kw value, 10 to the minus 14. And we're sort of, this is subbing for both of those last K values. Anyway, pKa, let me finish this up, is going to be the pKa for here, which is 1.8 times 10 to the minus 4 is the Ka. pKa is 3.74. Filling in all my units there, I have 2 1,000ths of a mole of both the formate and the formic acid. These two divide by each other to make 1. Log of 1 is 0. pH equals 3.7. And that one is now done. Marissa?
So what we're trying to do is just find pH 7, and look at which volume.
Question, so what are we trying to do with this, right? And so for a titration, we are going to figure out at the equivalence point what happens. Question is, and the equivalence point is when the pH is 7. Boy, do I have a surprise for you. Because the equivalence point will not be at 7 this time. I know. And that's where we're going, because here's what happens. You, every single time, what do I have? How does it react? Does it react to completion? Then what do I have left? Oftentimes I have a buffer. Okay? So it's the right question to ask, but I have a surprise for you, and for everybody involved. Any other questions about this? Travis?
Just the pH from the first part to the second part,
Yes.
obviously it has increased.
pH has increased.
So what the information is that telling us? Like, because are these two like problems related? Obviously, they're related, right?
So perhaps I can try and answer how are these two problems related, okay? And what we will see is, so we're in the process of constructing another pH titration curve, this time with the weak acid. And what we have already found is that just for the weak acid, before we add any sodium hydroxide, the pH was higher. And now what we've found is that as you titrate, you have a buffer. More surprises coming.
Okay.
Okay? I know, I don't want to, no, nothing up my sleeve. But does that,
Yeah.
so, yeah, so, yes. I don't want to give away all my secrets. Yes.
It's just on the other side.
Continue calcs. Ah, there we go. Thank you, Marissa. Now let's answer your question. So I'll write it over here, but now we're going to do 40. 40 milliliters of 0.1 molar sodium hydroxide have been added to 40 milliliters of 0.1 molar HCOOH. Do you know what we call this point? Hint, hint. The equivalence point. And so this is where things get a little crazy. Okay, so we know this is going to be the equivalence point. And Marissa?
So the equivalence point is the same volume, so that it's strong base and that is the same volume with weak acid.
Good question. When is the equivalence point? Well, when the concentrations are the same, then the volumes get to be the same. But if the concentrations are different, right, because equivalence point will always be in terms of moles. Okay? Does that answer your question? Yeah. And I just made the math easy this time on us. Do you believe me, we're at the equivalence point? That we've added equivalent moles of acid and base? All right. Now, I'm still going to do that mole ice table because it's a good practice, and you won't always know. Like, if these were different molarities, you may not know when you're at the equivalence point, but the mole ice table always proves it. Our process, remember, we have some weak acid, we have some strong base, those will react to completion. Ignore your sodium ion. So, same reaction. We're going to have moles. Set up our ice table. Now, these two numbers will be the same. And we went back to the beginning. So there's no formate ion. And I think that's the best way to go with these. Both of these are a limiting reactant. We have approximately 0 of each of them. Okay. Now, that is the completed ice table. At the end, or at equilibrium, or whatever you want to call it, what do we have? We have formant. What is formant? Is it a weak acid, a weak base, a strong base, an inert acid, inert base? It's one of those. It's a weak base. Right, we know that from the previous buffer example, and we need to be able to look at these things and say that by the second exam, right? That's our goal. One of our big goals is to be able to look at something. Okay, now, if it's a weak base, and what else do we have? Water. We only have two things now. If you have a weak base and you have water in solution, will the pH be less than, equal to, or greater than 7? It has to be greater than 7, and we're at the equivalence point. So the surprise, woohoo, is that the pH is greater than 7 now, but we know that because we know we have a weak base. And so that's the goal of this, even if we knew what the answer was going to be, was to systematically find out what's left. And if this were Chem 400, we would do it with stoichiometry, and that's a fine way to do it too. But my brain likes fewer boxes, and so I put it in, reaction goes to completion, just do this, and then think about it. So we have a weak base, we have water, those are the only two things we have. So pH must be greater than 7. Solve weak base, or solve KB ice table for formant. Because there's still, I know it seems like there's a million options, but there's still not really that many options. There was Ka ice table initially. There was buffer. Buffer, yeah, this is still buffer, good. And then there's Kb ice table. Because the only things you can have here are weak acids, weak bases. Well, we'll talk about that next. All right. So now I'm going to write a Kb reaction for formate. Kb reaction goes like this, H plus. Oh. If we're going to do a Kb ice table, Kb is in terms of molarity. We need a molarity ice table. We don't know the molarity of our formate ion. We know the moles of our formate ion. And we know that we've added 40 milliliters and 40 milliliters for a total of 80 milliliters. So we can get that concentration. And if you'll remember, this is actually very similar to some of the things we did last semester when we did titration problems. That looks like it should be a small whole number. Yes, it is. So I did that division right there. I ended up with 0.05. I subtract my x. I have my Ka value from previously. Now I'm looking for my Kb. My Kb value is right. This time I'm very happy to say I can safely ignore x when it's subtracted from this number right here. My x this time is my concentration of hydroxide. Which I get as 1.7 times 10 to the minus 6. That's a molarity. Yeah. I can find my pOH and then my pH. My pOH is 5.78. And my pH is 8.22. And just to be clear, this is at or equivalence point this time. And I'm very pleased to say that we do a titrations lab. We very physically will see that all of this is true. In fact, we still have plenty of time, so let's graph this out now, what it looks like. This is for a weak acid, strong base titration. And what we said was that first off, our initial pH was above 2. 2.37 was the number, but this will be a schematic. What then happens, and I'll sketch it and then discuss, well, for this one, the equivalence point was 40, so I'll try and hit it in my sketch. There's an initial increase. Then a relatively flat. Oh, hold on. Oh, so I'll tell you what I'm trying to draw. I'm trying to draw a more gentle slope here. And then it's still pretty flat up here. Loosely speaking, this is what's called the buffer region. And if you look at the buffer region, it doesn't go all the way back. I mean, technically, as soon as you add some, you've got a buffer. But we defined a buffer as that range of 10 to 0.1 for the ratio of the weak base to conjugate weak acid, conjugate pair. Anyway, there's a buffer region right here. Your equivalence point, we just calculated it. 8.22. Not so bad, actually. Buffer region, by the way, means that there is some weak acid and some conjugate weak base. And then once you get past the equivalence point, well, you have strong base. And weak base. And I don't know if you remember me proving this last time, but if you have strong base and weak base in the same solution, the weak base doesn't matter. The strong base rules what the pH is. Anyway, but hopefully what you can see here is that there is a sort of more gentle slope coming into the EP, the equivalence point, and that is indicative of the buffer region. Travis?
This is gonna sound like a tricky question, but for the buffer region, I see the slope is starting to, or the slope is starting to increase right before it exits it. Would you see that in the actual buffer region where it's still being buffered, but since the buffer is running out, it is starting to exponentially grow, or is it assuming the buffer, at least the buffer region, that's also how it's exponentially grow?
I may not have captured it exactly, but this is true. So you can see it's relatively flat in the heart of the buffer region, although not completely flat because you add strong base to something, the pH is going to go up. But it does start to, on either end, you get steeper slopes.
Oh.
Yeah. Logan, and then David.
On the previous page,
Mhm.
we started the second table and made it a molarity table instead of a mole table.
Yes.
If we had done a mole table and then ended up with a mole of OH and then converted it to molarity, we'd still get the same.
It's a good question. I would say, first off, so the first thing to remember is this has to be a molarity table. That's because you're plugging into a KB where these terms have to be molarities. And I mean, if there was only one molarity and one molarity, then the liter units would actually cancel out. But since there's two molarities over here, it would make a difference. Yeah. David and then Marissa?
So for the initial point on the graph, is that what we calculated? The acid with the water at first?
Yes. So
Okay.
this is our 2.37.
So when we do that in lab, we will be calculating the initial solution in the beaker or whatever we're using,
Yes.
and then watching the pH graph.
Absolutely. Yeah, and that's why I'm saying this initial pH is actually not really part of the titration because you haven't had, and yet it is. And we will do this. This is exactly what we will do. We will actually add the sodium hydroxide. We will, before we add it, take the pH. We will see the buffer region. We will note when, and in fact, we will note the equivalence point as, it turns out, not a great picture of this, but the equivalence point is the inflection point on that curve where the positive or the slope stops increasing and starts decreasing again. I don't know, not so good. But yes, we're going to do all this stuff. Yeah. Marissa? Good question. Your question is, at this part, what are the strong bases and the weak bases? I don't think I I didn't bring a calculation for it. But let's imagine we come back to here and we added some more. That means this number is bigger. That means that we do have some hydroxide left over. And we have our weak base. What we will see is that whenever there's strong base and weak base, you focus only on the strong base because it will set the pOH and then the pH. And that we did actually a calculation last time because we exhausted our buffer and we had excess strong base and some weak base. Does that answer your question? Yeah. Any more questions? Travis?
Just for the calculation of the KB, we solved for KA on the previous, and then the KW was the first one that we did. Just trying to.
Oh, KW is always 1.0 times 10 to the minus 14. KA is on your conversion equation sheet.
Oh,
So that's where you find it.
thank you.
Any other questions? Yeah, and our goal is to be able, to know what an acid or a base, what kind of acid or base we have. Our goal is to this point, right? I'm sure we'll have more. If you have a salt, and I was looking at and helping some people with the homework 3, if you have an ionic compound that dissolves, also called a salt, you have to be able to take those ions apart and figure out whether they're strong acids, weak acids, strong bases, weak bases, because all of that affects this chapter as well. So as you do the homework 3, know that it has an effect on homework 4, and it will help you. So really, I mean, Chem 401, more than Chem 400, builds. And what we will see, and this is really almost the rest of the course in a nutshell. If it's easy to measure the concentration of something, you use KCs, or KAs, or KBs. It's easy to measure the concentration of hydroxide and hydronium with a pH sensor, so we do it. Next chapter, we're going to get to thermodynamics, and for reactions where you can't measure any of the concentrations, but you can burn the thing and see the change in energy, we'll measure the energy, and we're going to relate that to equilibrium. And then we're going to do electrochemistry. And for electrochemistry, where you can easily count how electrons move, we will use electron movement and changes in oxidation state to measure the position of equilibrium. This chapter, thermodynamics and electrochemistry, all deal with different ways of measuring equilibrium that are the easiest for those particular systems. And we will relate all of it back to KCs. Travis?
And those are the 3 chapters covered in the next exam.
Those are the next, so 16, 17, I don't know where the break is. 18 is on, so we'll cover thermodynamics on the next exam. And then electrochemistry will come afterwards. But it does all build. So I know you probably know this already, but this stuff will matter as we keep going. So anyway, I think that's where I'm going to stop. Any questions? I know we're a whole minute early, so use that time to relax.